Um, First of all, I would like you to welcome everyone to today's webinar. Uh, the goal really is to introduce design of experiment concepts and really to introduce a few different design types that we could encounter. I think most people or many people might be familiar with some of the fundamental, more simple designs, but I'd like to show and showcase and demonstrate some of the more advanced things that have been developed over the years that really might help, many different new users in different circumstances to actually employ these really, to me, very exciting approaches to experimentation. By way of personal introduction, my name is Richard Williams, and I've been a studies consultant now for about 8 years. But prior to that, I spent 38 years in the chemical industry, really focused on product and process development and improvement. By training, I'm a chemical engineer with a business degree. I'm also a Six Sigma Master Black Belt. And in my experience, I feel that design of experiments has really been underutilized as a technique for problem solving and process optimization. But equally, I think that DOE really should be the tool of choice to launch reliable products from the very start. And that's really the idea behind quality by design or even design for Six Sigma. And over the past 15 years or so, I focused on providing training for product and process improvement tools. And that really brings me, to today's webinar that I'm really happy to bring this tool set, to you. A bit of a warning though, this is really a big topic. Think of DOE as, like a 2-semester, 4-credit class, if you will. And we're going to spend an hour. So obviously we are only going to scratch the surface. Yet I really am going to present a tremendous amount of material in that 1 hour. I'm going to do 3 examples and run through those. It's always a challenge to do this webinar to get it all in, but I do, and I hope that you'll pick up enough information along the way to find it useful and helpful to decide how DOE could actually help you in your world. And along the way, we're going to give you some resources and opportunities to discover DOE on your own a little bit more completely after this brief 1-hour introduction to a lot of content. Okay, so that's really where we're going today. And I'm going to turn the camera off and focus on just the presentation itself here. So get my tools working. So to prevent audio disruptions, I have the attendees on mute. Now, during the webinar, if you do have questions, I do have the question box open. So not the chat, but there's one called questions. So if you do have a question throughout the webinar, hopefully a brief one that I can take the time to answer, please go ahead and ask that. And if there's anything a little bit more advanced or complicated, or specific to an individual user, I'll try to follow up with that after the course, after the webinar. There will be a recording of this webinar, and it will be posted to our webinars page within the next few business days. So out on Stady's website, under Learning Webinars, you'll be able to pick up a recording of this. If you find that there's too much too fast, you can kind of go through it again if you wish. Okay, so that's kind of a thing. Now, what I'd like to do, just to make sure that the technology is working and that you're out there and can hear things, there is a little reaction button. If you could raise your hand just to let me know you're out there and things are working, that would be very helpful. I see one. That's probably a good thing. Excellent. A few. Excellent. Super. So that it's always good to know early in the webinar as opposed to halfway through. So what we really want to do is, I'm going to assume that you have very limited awareness of design of experiment methods, enough to want to attend a webinar. That's good news. But I'm going to sort of start at the very beginning of why you would really want to do your experimentation through some sort of DOE approach as opposed to, one factor at a time or other approaches that we may be more familiar with. Then I will introduce Design-Expert, the study software, and I will introduce that by doing 3 case studies, 3 problems that we're going to use. And they're very different from one another, and we'll get into that shortly. So the idea here and why they're different is I want to make people aware of the different applications and design types that you could encounter. Many people may have heard of factorial designs. Yes, we will do a factorial design, but there are more advanced designs as well. There are responsive surface designs to optimize the system. There are specific designs for formulations and mixtures that we might want to think about. Okay, so we have this going on. I've done the raise hand, so we know you're out there. So we're going to be using Stady's Design-Expert software. Actually, I'm going to use the Stady's 360 version, which is really kind of a more advanced version of Design-Expert. All it really does is add other tools. Everything we're going to do today, however, could be done in the standard Design-Expert approach. Okay. Certain clients have asked for more advanced features, and that's present in 360. But the tried and true Design-Expert can handle the majority of situations. So by way of agenda, we will first of all look at, what's in it for me? Why would we even think about doing DOEs? Then we're going to demonstrate three types of cases. Like I said, we're going to do a factorial, where we're going to characterize the main effects and vital interactions. Okay, an interaction is when one factor depends on the level chosen for another factor. Response surface methods are geared toward really optimizing a system. Okay, so we're going to find out when and what they look like, when to use them and what they look like. And we have special tools for mixture designs, where we can learn to hit the sweet spot in a formulation to achieve our objectives. And optimal custom designs really is what we're going to look at. It's going to be a mixture design plus a process factor, a simple one called amount, and you'll see how that unfolds a little later. So we can combine not just mixture, but mixture plus process, because oftentimes the process lends its fingerprints to the final product as well as the formulation. So what's in it for me? Okay, so when we do, we as experimenters, or we as engineers, we as chemists, we oftentimes view the world kind of as a process, okay? And we have controllable factors and responses. And our job oftentimes is to come up with some relationship, some understanding of the controllable factors and how they impact, a response. Keep it simple. Let's imagine we're baking cookies in an oven. Well, the controllable factors might be things as simple as, time and temperature in the oven, or a categoric choice. What type of cookie sheet are we using? Which rack are we using in the oven? The responses now would be things like the taste of the cookie, right? Some 5 people give a score or something like that, however you choose to do that, but you might have some kind of response where you're going to try to figure out how to control your X's in order to maximize the flavor or the taste of the cookie. Or maybe the yield of the process. You don't want to burn too many, you don't want too many undercooked. A response could be yield as well. The problem that we have in the real world is that when we're trying to make those connections, we're also fighting the noise factors. Noise factors are things like, well, for example, the measurement system oftentimes is a contributor to noise. If I'm measuring the taste of a cookie, well, I have 5 taste testers, and they may or may not give the same response every time, even for the same cookie, right? So there's going to be some variation in how they value things. When we set temperature in a process, do we actually set temperature? Well, what we set is the temperature setting. What happens inside the oven might wander around. It might cycle. It might be, if we set it for 350, maybe it'll cycle between 325 and 375. So we think it's 350, but what the cookie sees is something different. And the response is kind of based on what the cookie actually encounters as opposed to what we set it for, right? So we're going to have some variation caused by a number of noise factors. So our job is to statistically figure out, does X impact Y, despite the fact that we have noise factors going on. Now, I say process here, but I put the little beaker over here, the little flask over here, to remind myself to mention that all of this applies to formulations and mixtures as well, right? It's not just the process. Sometimes you can evaluate the formulation, in which case your X's might be the percent of the ingredients in the system, right? You still have responses, you still have noise factors. So this whole story applies to formulation work as well. So a designed experiment then is a planned approach for determining cause and effect relationships, right? It's not just a happenstance collection of data. It is a very purposeful choice of data points that we're going to run. And this has been sort of driven by, mathematicians going back a century now, starting with Sir Robert Fisher, who had these clever ideas for how to use mathematical principles to kind of sort out what experiments should be run in order to come up with the answers that we're looking for, establish the relationships. It benefits from multi-factor testing rather than one factor at a time. So, maybe you're like me and we were taught that you have to only change one factor at a time, otherwise you can't understand the impact of things. Well, guess what? Design of experiments completely violate that and prove that, in fact, you do want to change multiple things, as long as you do it in a systematic way so that you can uncover the relationships and the impact of one factor on another. And that's really where we get to. And it turns out we can understand more about the system if we do it that way than you could ever achieve with one factor at a time. One factor at a time cannot identify something called interactions. And what are they? Well, interactions is when one factor depends on the other. So let's look at baking cookies, and we have this little plot. So we have the short cooking time is the dotted line, and the temperature goes from low to high, and we're looking at the yield, right? So we don't want undercooked cookies, we don't want overcooked cookies. So with the short cook time and low temperature, we have a low yield because we have some undercooked cookies. But as we increase the temperature, we follow the dotted line and we actually improve the yield. Okay, well that makes sense. But if we have a long cooking time, then we have a different situation. Well, at the low temperature with a long time, we have a high yield. But now as we increase the temperature with a long cooking time, we decrease yield because now we're burning some of the cookies. So that situation is called an interaction, where the impact of one factor, say the cooking time, depends on the set point of the other factor, temperature. Okay, one factor at a time experimentation cannot identify interactions, just mathematically impossible to do so. So that's why multi-factor testing is so important. We can identify these interactions, which turn out to be very common in the real world, and something that we really need to envision, that our systems will have interactions, and we need to set up an experimental approach that will identify them. So that's where DOE comes in, right? The multifactorial experimentation and its parallel processing gives us more information than one factor at a time ever could. And the statistics that we provide give us confidence in the findings, right? So when we say something matters, it matters because we can prove it statistically. So Design-Expert gives us an array of different experimental types that we could encounter. And a lot of times we like to think about the SCO strategy, the screen, characterize, and optimize approach, where maybe we'll screen for the vital few, right? So maybe we have 20 different factors that we think could impact the flavor of a cookie. Maybe 5 of them we know to be true, so we won't screen for that. But the other 15, we don't know. And so we want to do a very quick analysis to sort out, well, which of those 15 factors, are going to contribute to the impact of the taste of a cookie. So screening design can take us there. And then once we know the important factors, right, the 5 that we knew plus those that survived the screening, then we can do a characterization where we're going to more fully understand the impact of each factor plus the presence of interactions and their contribution. We can also do a response surface design to optimize for peak performance. Okay, so sometimes the ideal conditions are going to be, not at the low or the high level that we are going to explore with the factorial design, but maybe it's someplace in between. Well, we might want to use a responsive surface design to chase that down. We also want to point out that we have several different environments or approaches that we can target a designed experiment. The factorial, like I just mentioned, will be used to characterize the response surface to optimize. And then the mixture design, well, it's basically a response surface design that's tailor fit to address mixtures, and there's some specific things that we'll get into as to why a mixture design is necessary to explore mixtures as opposed to a standard response surface. All right, so I'll keep this slide brief, but the idea of the DOE process, it's not unlike any other experimental approach, but first thing we need to do is define what we're trying to do, and we want to do it in terms of our measurable responses. We're trying to improve the flavor of a cookie by, on a scale of 1 to 10, we want to improve, so what have you, right? So that's the goal. Then we're going to select the input factors to study, and that's really where you, the process expert, would be the one to do that, or maybe we also learn something from a screening design. Okay, but we select the input factors to study, the X's. Then we're going to help you in the software to select the design, what factors you're going to set up, and what levels you're going to run, etc. You get to do the hard part, right? You get to go do the experiment. We'll come back in and we'll help you analyze the results, diagnose the residuals, look for outliers, make sure your data hangs together correctly so you can reach the conclusions you need to reach. We'll help you interpret the outcomes using model graphs and other features. We'll optimize factors even when we have multiple responses. So I might want to have a cookie that tastes good, scores high on taste, but also a high yield from the process. So we might have multiple goals that we want to satisfy at the same time. So we can set up criteria to do that, and then we're going to test our predictive model through confirmation runs. The computer says this is going to be the right set of factor settings to achieve the best results. Well, we want to go prove that to be true. So we'll do some confirmation runs. And at the end, you probably get to pick how to celebrate. You can always invite us. We may want to help. But the idea is, if you get this right, you actually reach a conclusion that's very satisfying. All right, so let's actually get into the software and do some fun stuff. So we're going to look at a factorial design, and we'll see what that means. So here's our situation. I'm a chemical engineer, so pardon me, a couple of my examples are going to be in that world, but you are free to envision your world and what kind of factors would be relevant to you. But let me just kind of tell you what's going on. So we want to maximize the yield of a chemical reaction. And I'm looking at 5 different factors. I've got feed rate, catalyst, agitation, temperature, and in the headspace of the reactor, I can either have just air, or I can go through the bother and expense of inerting it by putting nitrogen in the top of the reactor. Okay, so we want to find out the impact of those 5 factors. So what we're going to do is we're going to do a factorial study. In a factorial study, what we will do is look at each factor at a low level and a high level, and we'll study those in combination with all the other factors at their high level and low level. Okay, so we'll look at all the different combinations in a full factorial design. So what we want to do, and we highly suggest that before we go conduct an experiment, we want to make sure that we're collecting enough data to have a reasonable chance at answering the questions that we're asking. Okay, and there's a couple of inputs to that. The first thing we want to know is this thing we call delta Y, and in this case we're going to pick 3 percentage points for the yield. What does that mean? It means that any improvement less than that we will deem as unimportant. So if we have factors that go from their low level to the high level and they generate a 2 percentage point increase in yield, we might not detect that with the amount of data that we collect. We might miss that. And we're telling ourselves, well, that's okay. What we want are the heavy hitters. 3% or more we want to discover. If it's less than 3%, we're willing to we're willing to forego the, that we might. Now we can make that number lower, make that delta y lower, in which case we might need more runs in order to get the statistical power we need. We also need some estimate of the noise in the system, but that would be, for example, and I'm not necessarily saying you should do this, but let's say you ran 10 runs at the identical conditions, and you look at the final results, right? They have some variation. You can calculate a standard deviation, and that would be the natural variation in the system when you try to do the same thing. Well, that's the noise, so that's the 2%. The 2%. There's a whole other, it's a longer story about where we might grab that information or estimate it without going through the bother of running 10 runs or something and calculating it. But that's really what we're trying to represent. All right, so I have these 5 factors, and we want to build a factorial design. So let me jump to the software. Get the right one here. Well, let's start at the beginning. So when we open up our software, this is Statis 360. Design-Expert is the sister product to it. If we want to create a new design, well, we would simply create a new design. And here's where for regular 2-level factorial designs, this is kind of the entry point of the first type of design you might encounter. On the left-hand side, though, we do have a whole menu of different design types, right? So a little later we're going to look at response surface designs, a central composite. We could look at mixture designs, but we're actually going to eventually look at an optimal custom design down here, where we combine a mixture, a formulation, together with a process factor. So we'll get into that later. But right now, we're going to look at a regular 2-level factorial design. 2-level meaning we're going to study each factor at a low level and a high level. And here's the table of options. So I have 5 factors, and I'm going to go all the way down to the white box, which is a full factorial where everything is tested in combination with everything else. And that will result in a 32-run design. Now, I'm going to give you a little heads up or a peek that right above it, there's one that's colored green, and it's half as much work. That's going to be an option. It's called a fractional factorial. And we may have good reason to want to run, it's a lot cheaper, and we may choose to do that if we have enough power, but we'll see how that works. So then we would hit the design. And this is where we would input our factors and information. So for example, the first one is feed rate. The units are liters per minute. It's a numeric factor as opposed to a categoric choice. And we're going to go from 10 to 15. Okay, so we will go through all of our factors and we would do that. But what I'm going to do is I'm just going to jump to one that I've already started. So let's go do that. I find the right one here quickly. There we go. So I have the feed rate, the catalyst, the agitation, etc., and everything is in at their low and high levels. And what we're going to do is just explore the corners of the design space, nothing on the interior. The last one is a categoric one. So there's a little drop-down menu here, and I can pick numeric or categoric. And that one is just going to be nitrogen versus air. It's not a numeric value. It's it's either nitrogen or it's air. Then we would hit next. This is where that power calculation happens. Remember, we had that delta y of 3, and we had a noise in the system. It's going to calculate this little ratio. 3 divided by 2 is 1.5. And that drives the next screen, which is the power calculation. So what is this saying? It's saying with the 32 runs that we're collecting, if any of the factors, A, B, C, or D, all of these factors, if they turn out to be important, we have a 98% chance of detecting that. Okay, that's pretty good. We want to be at least 80%. The little blue boxes in our software are kind of giving you the key information you should be looking at any given screen. So this is saying we want that to be at least 80, and we're good. So we're going to continue and finish this design. So this is a lot of work. So this is 32 runs, but this is what we have in this full 5-factor factorial. In the real world, I would probably try to abbreviate that using one of the other options, either that green one, or we also have a minimum run resolution 5, but that's too much information for today. I will simulate this and get the data for this. And this one is reactor. And we have data, right? So that's the hard part you have to go do in the real world. For me, it was a little easier today. We now have data for all 32 runs. When we have data, we come down to analyze it. So underneath analysis, I have one and only one response in this case. So we will click on that. I will start the analysis. In this, we've made some easy graphical approaches to decide what factors matter and what ones don't. Oops, didn't need to do that. I want to select these little squares off to the right. So here's what's happening. The red line represents the best estimate of what noise is in the system. So any factor, these are all different factor types, right? So I could look at this one right here. That's a two-factor interaction between C and D. Well, that's sufficiently close to the red line that we're going to say that that is statistically unimportant, right? It's essentially equates to noise in the system. All these other factors and interactions are to the right of the line, and they therefore are statistically significant, right? B is the most significant, and there's two-factor interaction. The least significant one that we found was atmosphere. We can double check that on the Pareto chart, and we see with these statistical limits that we have here, the Bonferroni and the t-value limit, that everything we selected towers above the statistical test. So we feel pretty confident about the terms and the factors and interaction terms that actually belong in our predictive model. So once we're here, we're going to click on the ANOVA, the analysis of variance. So in our courses, we would go through a great detailed explanation for how these tables get created, but the blue box for now is going to tell us what we really need to know, what we need to take away. The key is the model is statistically significant. Okay, it's that easy. We're going to just kind of tell you that it's significant. The p-values being all less than 0.05 for all the factors and interaction terms chosen indicate that each one of the things that we selected on the half normal plot, this back here, this half normal plot, those are all statistically significant, right? So it looks like we've done a pretty good job of creating a predictive model. Now, just so you know, down here in the bottom we have these equations, coded equations and actual equations, but the key is we are creating these predictive models based on the data that we've collected, and those predictive models include all the statistically significant terms. In the upper right, we have fit statistics, and this is telling us more. We can look at the blue box to find out what's important. But we're given, R-squareds of various flavors and types. We like to look at adjusted and predicted. We like those to be high, obviously. We also want to make sure the difference between the two is less than 0.2. That if it's greater than 0.2, we may be including predictors in our model that aren't really necessary and they're perhaps unhelpful. If you include things like phase of the moon, it's just going to, mess up your predictive equation. It won't be helpful. Adequate precision being 37, that needs to be greater than 4, so we're in pretty good shape. So then we move on to the diagnostic plots. This is where we might look for outliers in our data, or we might want to look at whether or not we need something like a data transformation, which would be like taking the log of our data before we analyze it, or something like that. A lot of times we'll look at the residual versus run and make sure that we don't have anything outside the red statistical limits, which might be deemed as an outlier that we should chase down and evaluate further. But we're good in this shape. So we can go to the model graphics. And here's a two-factor interaction plot. Remember now, in our ANOVA, we have two-factor interactions, a BD interaction and a DE, right? So B, D, and E are our significant terms, and we have two-factor interactions. So now when we want to look at, the impact of catalyst, for example, well, the impact of catalyst, well, it depends on the temperature, right? If it's at the low temperature, the impact of catalyst, matters, but not as much. But at a high temperature, it matters a whole lot. Okay, so that's what we're looking at. A one factor at a time you can look at one factor plots, and it's going to warn you that you're missing most of the story because it's involved in an interaction. But had you done a one factor at a time experiment, that's all you would have known. You couldn't do the interaction. But here, now we know that, hey, one depends on the other. Now, in this case, we have B, D, and E are the ones of interest. And we have a categoric. Here I have nitrogen versus air. So a lot of times what I'll just do is I'll look at both cases. All right. So the other two are already represented here. I have catalyst and I have temperature, and the third one is to explore is atmosphere. So what I might do is I might maybe I'll create a report. I'll take this graph and I will export it to Word, for example. I'm not going to do it right now, but I could export that graph to Word, and then I could take a look at the one for air, and I could right click on that, and I could export that to Word. I could build up a report. But the key thing here is, if you just look at the lines on the graph, and I want to maximize yield, well, air seems to be detrimental. It looks like I want to go with nitrogen because the results are higher. And I can just click on this up here, and I can see that I have an estimate of 93 for the yield, 93.6. So my ideal conditions would take me there. That's where I would want to be. Okay, so if we had more than an hour to do 3 case studies, there's a whole lot more I would tell you about that. But that is the kind of the fundamental, most important key points in doing a factorial design. Okay, so let me close that one, come back to this. So the key here is a full factorial design tests all possible factor combinations at their high and low level. They will characterize all main effects, 2-factor interactions, and even higher order interactions. In this case, we have 5 factors. You could evaluate all the way up to a 5-factor interaction. 4 and 5-factor interactions are highly improbable to exist, and a 3-factor interaction is extremely rare. So perhaps we're doing more work than we need to identify the interactions because some of those interactions are not likely to occur. And that brings us to the world of fractional factorials, and I'll mention that in the next slide. We also want to look at power, and that really gets at the probability that an experimental design will identify the important effects. Okay, and it's driven by that signal-to-noise ratio. We really encourage people to kind of go through the bother of making an estimate of the delta Y and the sigma, and to determine whether or not your experiment has enough power to find what you're looking for, because it's really disappointing to go through all the work of setting up and conducting a DOE and then sit down to analyze it and finding out that you never had a chance of answering the questions that you had because we didn't have enough power to the design. Now, a tip here is, in this case, we may very well have been able to go to the 16-run design instead of the 32. It would give us less power because the way you increase power generally is to increase runs. So you're going to have less power. In this case, your power would have been 77%. So you would have gone from what we have, 98% down to 77. That's less than the 80 that's desirable, but it might be worth saving the 16 runs and accepting that even though it's not ideal power, it's pretty close. If you're pretty flexible with your rounding, maybe it's 80%, but it's close. But the idea here is the green ones are good for characterizing, pretty good substitute for these full factorial designs in most cases. The yellow ones would be suitable for screening designs, and the red ones we really wouldn't use at all, except for maybe something called ruggedness testing. But that's a whole nother story. We have some webinars on all that if you're interested on ruggedness testing. Okay, responsive surface. Let's talk about that one now. So with factorial designs, you can only look at interactions, okay? And you're only exploring the corners. If you have 3 factors, you think of it as a cube. You're only looking at the corners of the cube. You're not looking at anything in the interior of the design space, okay? You're only at the low and the high levels for each factor. You can identify interaction terms, and that really indicates kind of a twist to the responsive surface plane, but it can't create a hill or a valley. Okay, and that's the shortcoming, because if the optimal conditions reside inside of the design space, right, something between the low and the high level of your factor, you may have, an optimal like this, and in which case you're going to need to have a little bit more sophisticated predictive model. We may need to add these a squared and b squared terms, quadratic terms, in order to create the hill or the valley in the design space. Okay. So when we really want to optimize something, we think the optimal conditions would reside inside the cube, if you will, inside the design space, then we're going to want to kick up to a responsive surface type design. So the way those get laid out, or at least one type of these, and there are several types, but the central composite design is probably the oldest and most used one. But we have the original factorial, where the blue dots, where every factor is tested at the high and low combination against all the other factors. We will add center points, and we'll actually replicate the center point, do it more than once, so we have a good idea what's happening in the interior of the design space. And then we're going to put these axial star points generally outside the face of the cube, outside the design space, and those are just going to help us estimate the quadratic terms more carefully, right? So we get a better idea of the shape of what's happening inside the cube with the response. That's a central composite. So we're going to do one of those. So here, we want to find conditions that maximize the conversion of a reaction, and also keep another property called activity within its target range. So think of activity as maybe a functionality on the molecule that's desirable. We have three factors: time, temperature, and catalyst. And we want to achieve 80% conversion at minimum, and an activity between 60 and 66. And we'd like 63. If we could get 63, that would be ideal, but it has to be between 60 and 66. And we kind of think that the optimal conditions are most likely to be in the interior of the design space, the interior of the cube formed by the blue dots. Okay. All right. So here's what we're going to do. We want to maximize conversion and target activity. We want conversion to be at least 80% and activity to be, as we said. So let me call that one up. How are we going to set that one up? Get to the right one here. I think it's this one. Yeah. So here what we're doing is we're now, let me show you where we found this. So instead of going through the factorial now, in the menu path, we're underneath responsive surface designs, and we're going to pick the central composite, right? There are other choices, box bank and optimal, etc. We're going to look at the central composite, probably the workhorse of many response surface designs. We have three factors: time, temperature, and catalyst, and we put all those, the minimum and the maximum, etc. There's a lot of other switches here that we could put in there, but we're going to just accept the defaults for now. We'll click next to build this up. I have two responses this time, not just one: conversion and activity. And we're going to finish it. So here we have our design. Okay, one thing I didn't mention before is in the last example, is we have standard order and run order. So the standard order, it's in a very specific layout, but what you end up with is you have some factors that are kind of clumped together, and that can be a problem. It can be impacted by something called lurking variables, things like maybe the atmosphere temperature or atmospheric humidity, or just any other number of things that could drift throughout the sequence of runs. So in order to minimize the impact of that, we're going to have a random order to things. So we're going to have a run order, and that's going to shuffle the deck, if you will. And so we don't see as bad of an influence from these lurking variables. It sort of mitigates the problem to some degree. So randomizing the runs is very important in all DOE. Okay, let's get our data. I have another simulator for that, and this will be reaction. And we get data. See, it's a lot easier for me. So we have data. Well, we know what we need to do now. We have to analyze both. So we're going to come down to analyze. Let's start with conversion. I'm going to start the analysis, but something's different now. We no longer have the half normal plot to detect the factors of significance. Instead, what we're doing is it's identifying what mathematical model is going to best map to the data. And to make a long story short, we're going to accept the suggested value of a quadratic. So we will come to the model, and we can see that these will be all the terms that will be included. M means they're in the model. So we're going to accept those, and we'll jump now to the ANOVA. And here we have a significant model. Because we did replicates of the center point, we can do something called a lack of fit test. And what's that about? Well, we like our models to fit. Therefore, we don't want a statistically significant lack of fit. It's kind of statistical inverted doublespeak. So this is a good condition. We want the lack of fit to be not significant. Okay, so we're okay there. Right, so we have a good model to use to navigate the design space. Fit statistics are good. The blue boxes are content. We'll look at the diagnostic plots again. We have the same plots. I got one data point over here that looks a little funny, but it doesn't seem to be a problem in the residual versus predicted. It doesn't seem to be a problem in the residual versus run. So I can also look at some other things down here in the bottom. Maybe I'd take a look at, if I have a questionable data point, I want to know, well, does it matter too much? And then the bottom right, I have these influence charts, and I can look at Cook's distance or maybe difference in fits, and that's within the blue line. So even if that data point was a little bit off or weird or somehow anomalous, it's not doing much damage to my predictive model, so I'm just going to forge ahead. And then I can have these response surface graphs. It's always fun to see a 3D graph of that. So here's my 3D graph. You can see that I have some variation of my individual data points. But if you look at as I change the catalyst, you can see that the behavior of that curve changes substantially. Right? There's a lot of interactive behavior taking place amongst these three factors. Okay. But we've modeled it. We'll do the same for activity. I think this one turns out to be much simpler. It's just a linear model. And we can look at the ANOVA on this one. And here's a little interesting thing that I'll point out. If you look at the p-values for the three factors that are A, B, and C, we're looking for p-values that are 0.05 or lower to be statistically significant. 0.05 would be 95% confidence that it's statistically significant. 0.34 wouldn't make the cut. So B might not be a very good predictor. Okay. If I look at the predicted R squared at 0.9276, that's my best read on how good this predictive model is going to be for future cases, 0.9276. So let's just kind of keep that number in mind. What I'm going to do is I'm going to go back to the model and I'm going to take out B. I'm going to eliminate temperature as a predictor. So I still have a significant model. I have a not significant lack of fit. And the predicted R squared ever so slightly improved. The key here is it didn't get any worse. So sometimes if we reduce our models, we take out predictors that are not statistically significant, we can actually improve the utility of the model. Okay, so that's an important principle that we're going to see in the next case study. And we can look at the diagnostics, and we can look at the model graphs, and that's all well and good. But now that we have these two responses modeled, well, now we can seek out the optimal conditions, and that's where we're going to come down to numeric optimization. And now what do I want to achieve? Well, I want a conversion. What did we say? We want to maximize conversion. So I put that as the criteria. We said that we wanted to be at least 80. And I guess if I could get all the way to 100, that would be a good thing. So I'm going to make this little ramp. It says I want to get to at least 80 and as close to 100 as I can get. Activity, we had an interesting thing. We actually liked the value of 63. So I'm going to target that. I'm going to target the value of 63. But we said we wanted it to be at least 60 and no higher than 66. Okay, so we create this little ramp down here. I want to get to at least 60. 63 is ideal. And then 66 would be, we don't want to go any higher. So I have my two criteria, and now it's going to simultaneously try to pull those two together and come up with the best answer. And we have other tools and tricks. We can make one goal more important than the other with the number of stars that we give it. We can change the shape of the ramp if we wanted to kind of bias the answers to a given direction. Let me set that back to the original 1.0. And in the course, if you were to take a course with us, we'd walk you through the use of those kind of tweaks. But in the meantime, we'll just kind of take it as we entered it. And we have a solution now. If we look at the ramp view on this, here's the time, temperature, and catalyst that would deliver the best balance between the two objectives. We could hit a conversion of 91, and we pretty well nailed the 63 activity, right? So we were able to find the optimal solution with, in this case, two criteria. Okay, so let's see, get back to the slides. So response surface designs are useful when we expect curvature or nonlinearity inside of the design space, inside that cube framed by the factorial blue dots in this case. The model terms include quadratic or higher order terms in addition to the main effects. Okay, so we're not limited to quadratic, we're not limited to squares. We can actually do designs with our optimal designs that include cubic terms or quartic terms, etc. Okay, so that's possible. Things like the central composite really focus on quadratic, but it is possible to explore higher order models as well. It usually takes more data, so we like to avoid that. We will have more runs for an RSM than for a factorial. So you get more information, but you do a bit more work. We have numerical and ultimately graphical optimization tools, to find the optimal conditions to satisfy one or more criteria. We sort of saw a little bit of how that works. If your world is process, and these are the types of tools that might be helpful to you. If you're interested in additional training, we have both distance learning courses, public courses, and if you have a group at your company that you'd like to have us come and do one of those or do it through distance, we do have courses. Modern DOE for process optimization, where we spend, I think it's 2.5 days now total. The distance learning is 5 half-day, and the in-person is 2.5 days at your location. But we will make you quite skilled at using these tools. So that's an offer, just something to be aware of. Mixtures, specialized tools to hit the sweet spot. So here we have, in the mixture world, we have the factors are ingredients, okay? And the response is a function of proportions, not absolute amounts. So the idea is, if you think of one key ingredient, it would be the ratio between that and the key ingredient. So you might have 10 ingredients in the thing, but if I know the percentage of 9 of them, I can calculate by difference the 10th one, right? So it gets a little bit different. You can't use a straight up factorial design, and that's really what this graphic is showing us. If we did a factorial design, everything at the high and low levels, and I'm making lemonade from lemons and sugar water, well, I would look at the low. I'd look at 1 lemon and 1 glass of sugar water. Then I'd look at 2 lemons to 1, and then I'd look at 1 lemon to 2, and then 2 to 2. But the problem you run into is, yeah, but wait, The bottom left and the upper right are actually the same formulation. The only difference is I have laminate, right? So that kind of implies that there's an implicit problem if we use factorial designs or standard response surface designs when we try to evaluate mixture designs. So so for lemonade, maybe we could look at a ratio, right? If you look at a one-factor design where you have the ratio of lemons to sugar water, that might make some sense. So instead of 2 factors, you reduce it down to 1 factor, and that would be the ratio. If I have three components in a mixture, well, I'm not free to independently change because if I know 2, the third is calculated by difference. So now with three components in my formulation, I don't have a cube anymore. I have a triangle. So if I know 2 ingredients, the third is calculated by difference. Okay. So we have to use special tools to handle that. Our predictive models involve something called Cheffe polynomials. The design space in the software is created ideally to map to the type of designs that we incur with mixtures. So we're going to do, the third example we're going to look at is not only a mixture design, but is mixture combined with a process factor called amount. So think of it like this. Fertilizer not only depends on the formulation of the fertilizer, but it depends on how much you use, right? Paint coverage. It's a function of both the proportions of the ingredients and the thickness of the coating that you apply. Medicine, you might need an Excedrin after this webinar. Medicine, its effectiveness is a function of the proportion of the ingredients, right? Excedrin is, what is it? Aspirin, acetaminophen, and caffeine. So it's a function of the ingredients and their proportions, but it's also the dosage. You can have 1 or 2 tablets. So, so medicine is a mixture plus an amount environment. So here's what we're going to do. In a few minutes that we have left, this is a fun little example. We're going to make an ibuprofen time-release coating. Okay, so we have ibuprofen tablets, and what we want to do is put a coating on those so that they achieve a certain time-release property. We want this. We want I think it's 30% dissolved in 1 hour and 90% after 12 hours. And that's going to be the goal here. So, and what we're doing is we have a formulation. I have 3 ingredients in this formulation that we're going to play with, and that'll comprise 31% of the total formulation. The other 69 is going to be, maybe it's like water or some surfactants, what have you. But the idea is these are the 3 that we're going to change, and they will sum to 31%. And they will be varied in the ranges specified. Okay. Then what we're going to do is we're going to take whatever formulation is specified, and we will put some tablets, ibuprofen tablets, in a laboratory mixer, a coater, and then we will inject 15 to 25 milliliters of this mixture into the coater, and then we'll measure the time release properties of the resulting tablets. Okay, so here's what we're going to do. We want to optimize the coating formulation and the amount, and we want to make sure that we have target 20% release after 1 hour and 90% after 12 hours. So how do we do that? So we have way in the bottom of our list. So let me broaden these out so you see where I'm going here. Let's see, space filling. No, that's not what I want. Standard designs. We have mixture designs, we had response surface, we had factorial. So way in the bottom of the list under custom, we have a very broad and flexible type design. Okay, so here we can't use this mixture design because we have this process factor called amount to deal with. So in our optimal designs, we have a very flexible situation. You can play with 2 mixtures, a numeric factor, multiple numeric factors, categoric factors. So here we're going to have 3 mixture in 1 numeric. So that's what we're going to use to build here. Now, in our software, if you look at the help, there's a really fun little example, kind of what I refer to as the final exam. If you can do this one, you understand DOE. But there's one called Lady Baltimore, and it's going to involve two different mixtures. It's a Lady Baltimore cake, and it involves a cake and a frosting. So there's a formulation for the cake, there's a formulation for the frosting. It has a numeric factor. That's the amount of frosting that you apply. There's even some categorics put in there, the type of flour that you might pick. So it's a very flexible type design that you can do. And let me just kind of point you in this for future learning. Here's a hint. In the software, if you hit help, you can see these tutorials, and one of them here will be, where do I see it? It's in here somewhere. I'm not going to spend too. There it is. Combined split pot. That's another story. Lady Baltimore. So you could click on that, and it'll launch a tutorial. And in the tutorial data, you can actually analyze it. There's one, Lady Baltimore. So it would let you do that. So there's a whole variety of learning opportunities here in these tutorials. Not just Lady Baltimore cake, but there's a whole bunch of different things. Response surface, chemical reaction, et cetera, et cetera. So that's one place to get additional learning, very helpful. I digress. Let's go back to this case study. So we have 3 mixture components and 1 numeric. So here's the mixture. It's going to total 31 weight percent. The balance of the mixture will be held constant. We have the 3 ingredients, and they'll all be varied somewhere in that span, in that range. We will come to the coating. We said we're going to use between 15 and 25 milliliters injected into the lab coater. We hit next. It's going to be an optimal design. So an optimal design is we're going to make one for you. This is not a standard, cookie cutter type design. We're looking at the inputs you have given us, and then what we will do is we will let the computer shop around, let the Design-Expert shop around for the best set of data points to run in order to make sense of your story. Okay, so we're going to just accept the defaults here and let Design-Expert do its thing. I have 2 different responses, dissolved in 1 hour, dissolved in 12 hour. I will finish that. And it's going to calculate a bunch of different designs and pick the winner, and here it is. So here we have all these different designs. Now I'm not probably going to go out there and measure 14.5554, so we do have a little thing where maybe we can round this. Round components, let's say I will round that to, I don't know, 1 decimal place might make more sense. So it's going to do that. And even this coating amount, I can't get 14.56. Let's say I'm just going to round that to the nearest whole milliliter, and that's good enough. Okay, so I will let that happen. So now I have more conveniently chosen values for these. Let's go get some data. And this will be ibuprofen. So boom, we have data. Well, let's quickly analyze the 2. The dissolve in 1 hour, what was our criteria? Well, first of all, we have to pick a model. I'm ahead of it. So let's figure that one out. It's going to make its own suggestion. We're just going to go ahead and accept it. We'll click on model here. Now, with these more advanced designs, we probably almost always have more terms than we should as predictors. And I'm going to let the software tell me which ones it should get rid of. And so I'm going to use some criteria. I'm going to do something called automated model reduction. This is a little bit more advanced, but necessary in these types of DOEs. So then I got to fix hierarchy, another story, and so boom. So at the end of the day, quickly going through model reduction and correcting for hierarchy, I am now left with this predictive model. It's a significant model. The lack of fit is not significant. Remember, those were the ideal circumstances. My fit statistics are amazing. I will look at the diagnostics. We can get to some model graphics on that. And let's do a 3D just for fun. So here's the 3D, and let's see what happens. If I lower the coating, yeah, I'm getting more to dissolve. That makes sense. I don't have as much coating. If I increase the coating, I get less dissolved. but also the shape of that response surface changes as well. There's some interactive behavior between the coating amount, the process factor, and the formulation, right? So we're modeling that behavior between the two. Okay. All right, let's do the same thing briefly with the 12-hour. We'll start that analysis. We'll accept the standard. I'm going to simplify the model with model reduction. And if I hit ANOVA, okay, here we go. So we have a significant model, not significant lack of fit. Fit statistics are good. The diagnostics look good. I can look at model graphics if I want to. We could do the same thing, I suppose, and look what happens. You know, does it make sense that if I increase the coating, less gets released? Yeah, it does. So it makes some sense. Once I have my two responses analyzed, well, now I can optimize between the two of them. And what do I want? In 1 hour, I want to target the amount dissolved. We want to achieve, what did we say? My memory and my notes. Where are we here? I'm going to have to look this up. Don't want to do it wrong. We want to target 20. That's what it is. So we target 20. Then we want to go no less than 10, no more than 30. So we have this little ramp here. Then in 12 hours, we want to target 90. And we want to be no less than 80 and no more than 100. Okay, so those are the two ramps. And now I can look at solutions. And here's what we have. We have a formulation specified with the amount of A, B, and C in the material, the coating at 18, and that will give us a timed release capsule that delivers roughly 25%, so it's in spec in 1 hour, and about, 87%, so that's after 12 hours, so that meets the requirements for the timed release capsule. Okay. Timed release coating tablet, I think is a more appropriate term. Okay, so where are we? So mixtures have a built-in constraint. You know, the formulation has to sum to a total, and so we really want to tailor fit our design using a mixer design because it is, well, designed for that purpose. It's mainly used for optimization. In other words, it is a response surface design. Mixtures are a response surface design. But special approaches are needed to build the DOEs for mixtures. And so that's what we have using, like I said, Chef-A polynomials and other things to get it right. We can create custom optimal designs that combine mixture components and process factors, etc. So yeah, so this is kind of the putting the formulation together with the process all in one package. Okay. If mixture is your thing, if you do formulation type work, we also offer courses for that, mixture designs for optimal formulations. And once again, we teach those through distance learning, whether it's public or a private course. We can also, for 6 or more, arrange to have a trainer come to your facility if that's of interest. So in summary, a DOE is a planned multi-factor approach to efficiently and effectively determine cause and effect relationships and to find the optimal solutions, I should say. DOE statistics provide powerful and credible conclusions, right? We have the statistics packaged around our data so that we know that, you know, when we say factor X matters, that indeed it does, and that we have some confidence in what we're reporting. Design-Expert is a specialized DOE software. We have a wide variety of design types. We tried our best to kind of showcase those in a 1-hour format, which is admittedly challenging, but we went through a lot of material today to get that done. So here's our 2 software packages. Design-Expert is kind of the workhorse, and those that need more advanced features, we have the States 360. There are books available. I'll just kind of let you see those. These are rather lighthearted, in as much as you can make statistics a lighthearted topic. Mark in particular has done a great job of keeping these fun and interesting, and but these books do exist. These are the authors that participated from Studies. In our website, you can go out at studies.com. You can go out there and seek out industry specific success stories to kind of see how these tools get applied in a variety of circumstances. Mixture, coatings, pharma, etc. So there's a whole lot of different success stories out there. On YouTube, there's a tremendous amount of things now that are made available. A lot of our webinars and other training materials are available on YouTube. Like I said, we have white papers and other publications on our website. Within the software itself, the screen tips will give you some guidance. If you're looking at a screen, you're not sure what you're looking at, hit the screen tip and it'll give you some context-sensitive help. And I pointed out earlier that there are tutorials within the software in the help section that you can pull down and run through, a lot of scripts and guided training that would be available there. And of course, there are webinars on our website. You must have encountered that because you are here, but there are certainly many other webinars that are available and pre-recorded and live as well. That's it. So we're going to wrap this up now. I hope that you found this a little bit useful, or at least to understand the breadth of what DOE can handle. Hopefully something was relevant to your particular industry or needs. There's lots of options for additional training, like I just pointed out. YouTube has a bunch. Feel free to explore that and our other webinars. So with that, I'm going to conclude this, and I thank you for your participation and look forward to hearing your success stories in the future. So thank you very much for listening.